Hi all, I welcome you all to the next lecture. Today I am going to discuss about the second law of thermodynamics. So here Professor Ravi Kumar, Assistant Professor, School of Mechanical Engineering, Shastra DMTU University. So in previous lecture we have covered the first law of thermodynamics applied to the flow processes. Let's see today the second law of thermodynamics. The limitations of first law of thermodynamics was that in first law of thermodynamics we were not able to identify how much portion of heat is getting converted into the work, and as well as first law of thermodynamics says that whatever heat you are supplying to a system is going to convert it to the work. So total heat transfer is equal to the work transfer. That's what statement we have got from the first law of thermodynamics, right? When we are applying the first law of thermodynamics to a cyclic process, as well as the outcome of first law is internal energy. But here, as we are dealing with the open systems, in open system we cannot specifically define the internal energy. Second was there we were not able to identify the direction of heat interaction, what direction it is happening. That was another problem, limitation of first law of thermodynamics. The last limitation was we were not able to identify whether certain process or certain device is possible or not. That kind of information we were not getting from the first law of thermodynamics. That information will be accounted in the second law of thermodynamics. That's why there was a need for a new thermodynamics law, and this second law of thermodynamics came into the picture. So let's start our discussion for today. So I'm starting my presentation here. So the first question arises, right, whenever we are talking about why does heat flow from the hot lava into the cooler water. This is because this is a natural flow of heat. Basically, naturally heat should flow from high temperature into the low temperature. Why can't it be reverse? Why can't heat flow from low temperature environment to the high temperature environment? Is it possible? And another thing, is it easy to convert mechanical energy completely into heat? But not reverse. Why not? Why not? It's possible to convert mechanical energy into the heat, and sorry, heat into the mechanical energy fully. So these were the two biggest questions in front of designer, in front of thermal scientists. They were not able to understand why basically heat is getting flow from hot to cool. That is very clear. That's natural. Why can't we reverse? Why can't reverse things can happen? So that's why we need second law of thermodynamics and the concept of entropy to answer the above questions. Without the help of these two concepts, you cannot clearly say what is basically happening to the system. So what is basically second law? Let's have it. So second law, it identifies the direction of a process, that is heat can only spontaneously heat transfer from a hot object to the cold object. That is a natural way. Why not in opposite direction? So this talks about this, and used to determine the quality, right, of energy, and we clearly say that heat is a low quality and work is a high quality energy, right? So used to exclude the possibility of constructing that 100% efficient heat engine or perpetual motion machines. So it violates the Kelvin-plank and Clausius statement. These two statements I will discuss in detail in the coming slides. So as per the second law, complete conversion of heat is not possible. So that means we cannot say it is a 100% efficient engine where whatever you are supplying is getting converted to the mechanical work. So then finally the outcome of second law will be to introduce the concept of reversible process and irreversibility. How much irreversibility is that you come to know? So that will get defined in terms of entropy. That's irregularity will be measured with the help of entropy concept. So second law. So whenever we say naturally, right, naturally, if I say certain process is happening, that process is only possible if it satisfies both the laws, first or second law of thermodynamics. If any process or any device is going to violate any one of these law, is not possible, physically is not possible, right? So first law characterizes the balance of energy, which defines the quantity of energy, right? Second law will talk about the direction which process can take place, or it will be talking about the quality, how much quality of this thing is getting converted into something else. So it will clearly tell you an idea about what is a low quality, what is high quality energy. So when we talk about the heat engine is a device, basically it is designed to produce the mechanical work out of heat input. So you need to supply the heat input, out of that it will be generating the mechanical work output. So if we look at this kind of thing, it will be requiring minimum two bodies, one body at high temperature, another body at low temperature. So high temperature body, you can assume like it is a combustion chamber where you are generating the heat, and from there you are getting the heat, and that heat is getting converted to mechanical work, and rest of the heat need to be rejected, and where it will go, it will be going to the surrounding. So second, cooler temperature body will be your surrounding, and higher temperature body will be your combustion chamber. So if I draw a block diagram of it, it will be something like this. When a high temperature body is here and this is a low temperature body, and in between this is a cyclic device which that we are basically using to convert into mechanical work. So there is a heat input to the engine, there is a heat output from the engine. Why it's output? Because we are not able to convert the entire heat which is coming inside the engine into the mechanical work. So that the unused heat need to be rejected in order to start a new cycle. So that the heat is coming out to the surroundings. So this is going to the surrounding at T temperature lower, and we get the mechanical work out. So if we apply the energy balance, that is using the steady flow energy equation concept, we can easily find out what is the net work output. So if I say what is coming into this control volume, right, if I say QH is equal to W net plus QL, so I can say W net is equal to QH minus QL. So net work is nothing but the heat supplied minus heat rejected. The difference of this will give the net work. Then somebody will ask you to define what is the conversion thing, means so what is the efficiency of it. I will say it is a net work output which we got out of what we have supplied. So net work output divided by heat input will give us the conversion efficiency. This much amount of heat is getting converted to the work. So basic simple concept. We can apply the first law. Delta U will not be there in cyclic process, so W net is equal to QH minus QL. Simple way we can say. And so thermal efficiency can be defined W net divided by heat supplied. So that W net is QH minus QL divided by QH. So I can finally say efficiency is nothing but 1 minus QL by QH. So heat rejected, heat supplied ratio 1 minus this will give the conversion efficiency or thermal efficiency. So now question arises, can we produce 100% efficient engine, or can we have 100% efficiency? No, because heat transfer to the surrounding cannot be zero. If that is going to happen, then where you will be keeping that unused heat, so it will be another big issue to an cyclic device. So that is not possible in reality. That will not happen in practically 100% efficiency. So that's why two statement came. One statement was given by the Kelvin-plank, two guys, they gave the statement. The first statement was given by the Kelvin-plank. It says that it is impossible for any device that operates into a cycle to receive heat from a single reservoir and producing the work. That means minimum two reservoirs are needed to generate the mechanical work. That means one high temperature reservoir, another is a low temperature reservoir. These two reservoirs are needed, then only you can generate the mechanical work out of it. If we are saying that there is only one reservoir, from there it is getting the heat and we are generating the work, that is impossible. That is going to violate the second law of thermodynamics. This is the first statement. So if that is going to happen, that means our conversion efficiency 100%, whatever is coming in and we are getting the work output. So it is going to violate basically the one of the law of thermodynamics. So it is impossible. So it is a very simple statement they have given. It is impossible for any device that operates in a cycle to receive heat from a single reservoir and produce net work output. This statement is without proof. Basically, how it has until now no processes have violated it. So consequently, it is impossible to build a engine that is 100% efficient. So it is something like that. There is only one reservoir from where heat is coming to the heat engine. Finally, we are generating the net work output. So this kind of device is impossible. So keep in mind. So something has to be rejected to low temperature in order to complete the cycle. So next statement came Clausius statement. This fellow talk about the reverse direction of the flow from low temperature to the high temperature. So as per it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from low temperature body to high temperature body. That means when we are transferring heat from low temperature body to high temperature body, we need to do some external work on it. That means it will be requiring some work on it. If somebody is claiming that automatically heat is getting transferred from low temperature body to the high temperature body. That means such kind of process is impossible as per the second law. So similar to the KP statement, it is also a negative statement and has no proof. It is based on experimental observations and has yet to be violated. Till now, no one has violated these two statements. Keep in mind, if somebody is going to violate, this will be a new discovery. So heat cannot be transferred from low temperature to the high temperature bodies unless external work is supplied, right? So this is the thing. Automatically heat will not transfer from low temperature Hy to the high temperature Hy. You need to supply some work, right? So any device which is claiming like it automatically can do is going to violate the second law of thermodynamics. So now come to the heat pump and refrigerator. The heat pump is a device which maintains the body at a temperature higher than the temperature of surroundings, right? So heat pump is used to extract energy from outside, right, and cool outdoor air into the warm indoors. So in the colder day, right, and winter season, we use the heat pump to heat our room. So what it will do, it will take the heat from the surrounding and supply to the body. So body is your room basically. So if you look at the cyclic process, this is a cyclic device which is called heat pump and is taking the heat from low temperature body. So in this case, this reference body is our surroundings. You can see atmosphere, and this high temperature body is our room. Let's suppose we are heating our room. So this high temperature body is our room. So it is taking heat from the low temperature surroundings, and with the help of why? Because it's transferring heat from low temperature body to high temperature body. So we need to supply some work. So we have supplied the work. Network is getting supplied here, right? So this is a work consuming device. So the network came, and because of that heat got transferred from low temperature body to high temperature body. Even refrigerator also does the same thing. In that case, low temperature body is your body basically. That is your refrigerator. If you look at refrigerator inside, space is your low temperature body, and from there it will take the heat and it will reject to the atmosphere. So high temperature reservoir will be your atmosphere, and it will be supplying, we will be supplying the work, because that thing will be done by the compressor, and compressor requires some work input. So both heat pump and refrigerator are the work consuming device. Only difference is reference body. In the case of heat pump, reference body is our surroundings, and high temperature reservoir is your body, right, or region where you want high temperature. In the case of refrigerator, the region where you need low temperature is your low temperature reference body, and that heat is getting transferred to the surroundings. So refrigerator also same function. Difference between two is type of heat transfer, and that need to be optimized. So efficiency of heat pump and refrigerator cannot be defined like thermal efficiency. They will be defined by another parameter that is called coefficient of performance, right? Coefficient of performance. Where? So now coefficient of performance is nothing but what is the desired effect from the heat pump. From the heat pump, desired effect is a high temperature heat to be supplied to the room. That is our desired effect divided by the work input. So COP of heat pump, it is desired effect is our Q heat, right, that we need in a region. Q high divided by W net. This is not a coefficient of performance for the heat pump. Similarly, coefficient for refrigerator is desired effect is a low temperature a region. So QL divided by W net is the coefficient of performance of refrigerator. So if we do the rearrangement of terms, we can get these formulations. All right. So if we relate these two, right, we can get one formula, that is coefficient of heat pump is equal to coefficient of performance of refrigerator plus 1. This is the relationship, right, that we got by relationship of these two. So practical refrigerator, if you look at this is the practical refrigerator, right, in our domestic use we are using that. So if we go to the back side, if we say this kind of crisscross line, these are basically condenser lines, right, and this is the compressor basically. Here work is getting supplied from external cord, this electric work you are giving to it, and then it is performing the operation. So if we look at the total component in a refrigerator, there are only 4 components. One compressor is needed, and these are the crisscross piping through which your refrigerant will flow, and finally this is expansion valve, then finally it will come here, right, then evaporator, these are the evaporator coils, right, basically at the top of the refrigerator. These are the evaporator coil where cool air will come inside, right, from the atmosphere. It will absorb the heat, and because of that things will get cooled right here. So here cooling you will get, right, and finally it will return back to the compressor. Total 4 components overall if you look at. these are all needed. So compressor, right, followed by condenser, this is the condenser coils, right, and then followed by the expansion valve, then evaporator. These are the four things which are needed to perform refrigeration, right. This is called refrigeration cycle, basic refrigeration cycle. You might have got this idea from basic mechanical engineering. So perpetual motion machine, any machine which is going to violate the second law of thermodynamics, any one of those two statements. So first, imagine that we can extract energy from unlimited low temperature reservoir, right, source such as the ocean or atmosphere, right, and both brought to the thermal equilibrium. So if we say that this is only interacting with the one reservoir, that is ocean, at low temperature and getting heat and transferring to the high temperature surrounding without any work input, right, without any work input, so it is basically going to violate the Clausius. If you are making some more arrangement, if you are adding one heat engine which is taking heat from low high temperature reservoir and rejecting heat directly to the heat pump, right, not rejecting, doing work, I mean whatever work it is generating, it is applying to the heat pump, and as this is generating extra work, so some work is coming out. So this combination further will be carrying some sort of heat pump, heat engine, which is transferring heat from low temperature to high temperature body and generating some network. That is also impossible, right. So this is going to violate the Kelvin-plank statement, right. So any engine or device which is going to violate the second law of thermodynamics or any of the statement of second law of thermodynamics is not possible, and such kind of machine is known as perpetual motion machine of second kind, right. So perpetual motion machine are classified into two types. One is called perpetual motion machine of first kind, that is going to violate your first law of thermodynamics. Perpetual motion machine of second kind, which is going to violate the second law of thermodynamics. Now if we look at those two statements, we can put the equivalence between these two. How to do that? So if one statement is going to violate the another statement, we can say both are equivalent, right. So assumption of first is going to violate this assumption of second, so that will do parallelly. So it can be shown that the violation of one statement leads to violation of the other, and that's why they are equivalent. So let's assume there is a heat engine, right, which is taking heat from the high temperature source and generating the work, and it's not rejecting anything outside. That means it's violating the Kelvin-plank statement. That means there's no device which can generate work with the help of only one reservoir. So this is violating the Kelvin-plank statement. Now assume that there is a heat pump which is transferring heat from low temperature region to the high temperature region with the help of whatever work that has been generated from the heat engine. So this combination, if you look at this combination, will be working like a heat pump, right, which is transferring heat engine and heat pump. If we combine, this will become a single heat pump which is transferring heat from low temperature body to the high temperature body without taking into any work in the system, right. This is the boundary, so nothing is coming inside. So that means the combination is going to violate the Clausius statement. That means one statement that we started with violation of Kelvin-plank statement, and we made some arrangement of another heat pump, and we are directly attached with the heat engine. This combination further is going to violate the Clausius statement. So we clearly have seen that the violation of one statement is going to violate the second statement. So this combination will be something like this. This is another heat pump which is transferring heat from low temperature body to the high temperature body without taking anything inside. This is while violating the Clausius statement, right. Another scenario, if we look at, now assume a heat pump which is transferring heat from low temperature body to the high temperature body without taking inside anything, any work or something. So it is this one arrangement is going to violate the Clausius statement. Now assume there is a heat engine which is operating between same temperature source and sink, and it's taking heat from the high temperature bath, right. It is taking heat, whatever is coming from the heat pump, same heat is getting supplied to the heat engine, and finally it is generating the work output. So if you look at this, so whatever heat which is coming from the heat pump is getting supplied to the heat engine, that means there is no contribution from the high temperature reservoir. So this reservoir can be eliminated. When we are going to eliminate this reservoir, this combination of heat pump and heat engine with further combined together will forming a heat engine which will be transferring continuous supply of work with the exchange of heat only with a single reservoir. That means going to violate the Kelvin-plank statement. So we start with the Clausius statement and we assume a heat engine which is taking heat input, whatever is getting rejected from the heat pump. In that case, what is happening? There is no contribution of high temperature reservoir, so this can be eliminated. So this combination of heat pump and heat engine together constitute a heat engine which is transferring continuous supply of work output while exchanging heat only with one reservoir. And this is another violation of Kelvin-plank statement. So violation of Clausius leads to the violation of Kelvin-plank statement. And first case we have seen, then the violation of Kelvin-plank leads to the violation of Clausius statements. So we can say finally that both these statements are identical and both these statements are for the second law of thermodynamics. Any violation of one statement is automatically going to violate the second statement. Now if we come to the reversible process and irreversibility, a reversible process is one that can be executed in the reverse direction without leaving any trace to the surroundings, right? Without any loss of energy, right? Such kind of process is known as a reversible process. So at the end of forward and backward reversible process, both system and surrounding can be restored to its initial states, right? So in reality, no real processes are reversible. However, reversible processes are theoretically the most efficient process because no losses will be involved in this kind of processes. So all real processes are irreversible due to irreversibilities. Hence, real processes are less efficient than the reversible process, right? Keep in mind, what are the common sources of irreversibility? Why irreversibility comes into the processes? One is due to friction, because the presence of viscosity, right? Friction will occur, and sudden expansion and compression, these are the another factor. And heat transfer between bodies or with a finite temperature, they are having different definite temperature, between that heat transfer is taking place. That means the reverse is not true. So like if heat is getting transferred from high temperature end to the low temperature end, reverse is not true unless we are supplying some external work on it. So those all processes are irreversible. These are the different factors why which irreversibility comes into the process. So a quasi-equilibrium process, when we say this occurs very slowly. So each state passing through Y process is an equilibrium state, and any process which is happening very slowly can be considered as quasi-equilibrium process, and any quasi-equilibrium process can be made to reverse the direction without making any change to the surroundings, right, or to the universe. And such kind of processes are known as reversible process. So why reversible processes are needed? Always reversible processes. Things are very simple. A work producing devices which employs quasi-equilibrium process or reversible processes produces maximum possible work output. Maximum possible theoretically possible work output. A work consuming device which employs these kind of processes will require minimum work input because other losses will not be present. So minimum work input will be requiring if all the processes in a work consuming devices are reversible, right? So one of the most common idealized cycle that employs all the processes are reversible was invented by the Carnot, Sadi Carnot, in 1824, right? So that cycle is known as Carnot cycle. Carnot cycle is a hypothetical cycle that does not exist in reality. So yes, this is a hypothetical cycle. All processes are reversible. That means it's 100% efficient cycle. Efficiency of Carnot cycle is 100%, which will not be happening in a reality. Alright. So if we look at the Carnot cycle, which is something like this. So Carnot cycle he gave this idea. It's a piston cylinder device basically. So first process start with the heat transfer from hot reservoir. There is a hot reservoir through which heat comes into the piston cylinder. This is a system, right, gas, and to which we are heating from the hot reservoir, right? So hot reservoir gives the heat into this, and because of the heat, what will happen? Your piston will move. So basically heat temperature is constant here. Temperature of reservoir is not going to vary. So So temperature is constant, so whatever heat is getting supplied, irrespective of the heat going out or coming in, the temperature of reservoir will not change. So when we are defining a reservoir, thermal reservoir is a body of infinite heat capacity, right, which can transfer or can absorb unlimited quantity of heat without any appreciable change in its thermodynamic properties, and that is known as thermal reservoir. So that's why we are saying this is a reservoir. So reservoir, nothing change will happen irrespective of whatever heat is going out. So heat is coming here, that means heat is getting supplied at constant temperature, and because of that it will expand. Right, then immediately after that, once heat has been supplied, we will replace this boundary by a insulating boundary. So now this is insulated and further expansion is taking place. Now expansion become adiabatic. So it started with isothermal expansion, then adiabatic expansion. So once the work has been produced, now we will replace this insulating boundary by a conducted boundary, right, that is called cold reservoir. So now what will happen, piston will move down and heat will get transfer to the cold reservoir. So once the whatever heat has been generated gone out, we will replace this boundary again by a insulating boundary. This is known as adiabatic compression. Adiabatic compression basically is happening compression. So basically it is having four processes: reversible isothermal expansion, process 1 to 2, where temperature is constant and heat is getting supplied. The reversible adiabatic expansion 2 to 3, where heat transfer is 0, but temperature is still becoming low temperature. A reversible isothermal compression, right, where heat is getting rejected to the surrounding, right. So these are all different four processes will be happening between this 1 2 2 3 3 4, right. Process will happening, and last one is your adiabatic compression, right, reversible adiabatic compression, where heat transfer is 0 and the temperature is going towards high temperature end. So we represent that cycle over the pressure and volume diagram, which will be something like this. So this is basically a reversible adiabatic isothermal heat addition followed by the expansion. This is also almost adiabatic expansion, right. Then this is a compression, or you can say the reversible adiabatic heat rejection, then reversible adiabatic compression. So it is having four processes. Process 1 to 2 is reversible isothermal heat addition, process 2 to 3 is reversible adiabatic expansion, then process 3 to 4 is reversible isothermal heat rejection, and process 4 to 1 is reversible adiabatic compression, right. So it's the same thing if we represent here in a very simple way on PV diagram, which is something like this. So area under this curve, right, will be called as net work. So efficiency is known as work done divided by heat supplied. So work done will be QH minus Q lower divided by QH. We can simply say, so Q is CPT1, Q1 is equal to CPT2. So we substitute these values here, we can say efficiency thermal depends only on temperature, 1 minus T2 by T1. So you can say the efficiency of Carnot cycle depends only on the initial and final temperature of the cycle. It does not depend on the working fluid or properties of working fluid. So it is independent of the properties of working fluid. It depends only at the initial temperature and final temperature of the cycle. So Carnot theorem. So Carnot they gave one theorem. So as per the Carnot theorem states that no heat engine working in a cycle between two constant temperature reservoir can be more efficient than a reversible engine working between the same reservoir. That means actual engine cannot be higher efficient than a reversible engine. So reversible engine will be having maximum possible efficiency, not your actual engine. So this statement was given by the Carnot, Carnot, and this is known as Carnot theorem. Another word we can say, the all engines operating between a given constant temperature source and a given constant temperature sink, none has higher efficiency than a reversible engine. So reversible engine will have a high efficiency. So this theorem was given. With this I am closing the today's discussion. So today we have gone through introduction about the second law of thermodynamics. We have seen the limitations of first law of thermodynamics, and then we have seen two statements of second law of thermodynamics. We have developed a relationship between these two statements, and we have clearly proved that violation of one statement is going to violate the second statement and vice versa. We also defined the definition of heat pump, refrigerator and heat engine. We have defined the thermal efficiency and coefficient of performances of the work consuming devices and heat engine, right? And we have seen the idea of Carnot cycle. So Carnot cycle is the efficient possible cycle and that does not exist in reality. This is only for the sake of comparison. We compare the actual engine performance to a Carnot cycle, right, to define how much efficient it is, right. So with this I am closing today's discussion. If you are having any doubt in this topic, you feel free to contact me. You can write in the comment section, alright, provided in the video. So thanks for your patience, alright. Have a nice day. Good day.